Vector equation of a line. Welcome, everyone. Today, we are going to explore a fundamental concept in vector geometry, the vector equation of a line. To start, let's look back at what you already know from two-dimensional geometry. When we work on a flat 2D plane, defining a line is relatively straightforward. We usually just need a single point and a slope to describe exactly how that line behaves. However, as we move into three-dimensional space, the world we actually live in, the concept of a simple slope, is no longer sufficient. In 3D, a line doesn't just tilt up or down. It can tilt in infinitely many directions across various axes, making a single scalar slope value inadequate to capture its orientation. So how do we fix this? To uniquely define a line in 3D space, we need two specific pieces of information. First, a fixed point that we know lies on the line, and second, a direction vector that tells us exactly which way the line extends. In the next few slides, we will break down how we use these two components to build a complete vector equation. Conceptual understanding. First, we need a fixed point. Imagine we have a line, which we'll call L, and we know for certain that it passes through a specific known point, which we'll call A. To turn this point into something we can use in an equation, we use its position vector. This is the vector starting from the origin, O, and ending at point A, and we denote this vector, A, with an arrow on top. This gives us our starting location in space. Second, we need a direction vector. As I mentioned in the previous slide, a line in 3D can tilt in many directions, so we need a vector to guide us. We'll use a non-zero vector, which we'll call B with an arrow on top, that is parallel to our line. This vector, B, essentially acts as our compass. It tells us exactly which way the line is pointing. Finally, we need to account for an arbitrary point. Since a line is made up of infinitely many points, we pick any general, random point on the line L and call it P just like before. We represent its position using a vector starting from the origin, O, and ending at point P, which we denote as R with an arrow on top. Now that we understand why a simple slope isn't enough in three-dimensional space, let's look at the specific components we need to build our equation. Think of this slide as defining our ingredients. In the next slide, we are going to use these three ingredients, our starting point, A, our direction, B, and our moving point, R, to mathematically derive the actual equation of the line. Step-by-step derivation. Now that we have identified our key components, the fixed point A with its position vector, A, the direction vector B, and our unknown point P with its position vector, R, let's walk through the mathematical derivation to see how they all come together to form our final equation. In step 1, our goal is to find a vector that connects our known starting point to our unknown point. We look at the vector AP, which represents the displacement or the movement from point A to point P using the triangle law of vector addition. We can express this displacement by subtracting the position vector of our starting point from our destination. In other words, vector AP equals vector op minus vector OA. Since we've already defined vector op as R and vector OA as A, we can simplify this to vector AP equals R minus A. Moving on to step 2, we need to link this displacement to the direction of the line. Remember from our previous slide that the line is parallel to the vector B. Because the vector AP lies directly on this line, it must also be parallel to vector B. In vector algebra, if two vectors are parallel, one must be a scalar multiple of the other. This means we can write vector AP equals lambda times vector B here. Lambda is a real number, or a scalar. Think of lambda as a scaling factor. As it changes, it stretches or shrinks the vector, allowing us to reach every possible point P along the infinite line. In step 3, we bring these two ideas together. We take our result from step 1, where we found that vector AP equals R minus A, and substitute it into our equation from step 2. This gives us the relationship, R minus A equals lambda times vector B. Finally, in step 4, we want to isolate our target, which is the position vector R. By simply rearranging the equation, adding vector A to both sides, we arrive at the final vector equation of the line. R equals a plus lambda times vector B. This elegant formula tells us that to find any point on the line, you simply start at point and move some distance, scaled by lambda, in the direction of vector b. This is the foundation we will use for the examples coming up next. Real-world analogy, the flight path of a drone. Oh, I know the mathematical derivation we just went through in the previous slide might seem a bit abstract, so let's bring this concept into the real world with an analogy. Imagine you are operating a drone. Suppose the drone takes off from a very specific GPS coordinate, which we can call point A in our math notation. This starting location is represented by the position vector, Once the drone is in the air at that point, it is programmed to fly in one constant, unchanging direction. We can represent this direction using the vector b. In our math notation, this starting location is represented by the position vector, We can represent this direction using the vector b. Now, as the drone flies, it covers different amounts of ground. The distance, or the scale of how far it has traveled along that path, is represented by the scalar lambda. So, if you want to find the drone's current position at any given moment, which we call the position vector r, it is simply a matter of taking its starting position, and adding the distance traveled in direction b, scaled by lambda. This gives us our complete formula, r equals a plus lambda times b. This visual helps us see that the equation isn't just a static formula, but a way to track movement along a path. Now, let's see how we can apply this logic to solve some actual mathematical problems in the next slide. Worked examples. Now that we have understood the concept through the drone analogy, let's put that theory into practice with some concrete mathematical problems. In our first example, we are tasked with finding the vector equation of a line. We are given a specific point, 2, -1, 4, and we are told that the line is parallel to the vector, 3i plus 2j minus k. To solve this, we follow a clear four-step process. First, we identify the position vector, which we call a vector. Since the line passes through the point 2, -1, 4, our vector is simply 2i minus j plus 4k. Second, we identify the direction vector, or b vector. Because the problem states the line is parallel to the vector 3i plus 2j minus k, we can use that directly as our b vector. Third, we apply the fundamental formula we derived in the previous slide. R vector equals a vector plus lambda b vector. Finally, by substituting our specific values into the formula, we arrive at our result. R vector equals the quantity 2i minus j plus 4k, plus lambda times the quantity 3i plus 2j minus k. Now let's look at a slightly different scenario in our second example. In this case, we aren't given a direction vector directly. Instead, we are given 2 points, point A at 1, 2, 3, and point B at 4, 5, 6. The logic remains the same, but we have one extra step to determine the direction. Step 1. Identify the position vector, a vector. We can choose point A as our fixed starting point, so our vector is I plus 2j plus 3k. Step 2. Find the direction vector, b vector. Since the line passes through both A and B, the direction of the line is the vector from A to B, which we denote as ob vector. To find this, we subtract the position vector of A from the position vector of B, that is, 4i plus 5j plus 6k, minus the quantity I plus 2j plus 3k. After performing the subtraction, we find that our direction vector, b vector, is 3i plus 3j plus 3k. Step 3. We apply our standard formula, r vector equals a vector plus lambda b vector. And step 4. Our final result is r vector equals the quantity I plus 2j plus 3k, plus lambda times the quantity 3i plus 3j plus 3k. As you can see, whether you are given a direction or 2 points, the goal is always to identify your starting location and your direction. In the next slide, we will summarize the key takeaways to ensure you have the essential components memorized. Key takeaways. To summarize, the fundamental formula you need to memorize is r vector equals a vector plus lambda times b vector. It is crucial to remember exactly what each component represents. First, the vector is the position vector of a known point on the line, Think of this as your starting or fixed location. Second, the b vector is a vector that is parallel to the line, which we call the direction vector. This tells us the path the line follows. Third, we have lambda, which is a scalar parameter. This is a very important part of the equation because lambda varies for every single point on the line, allowing the line to extend infinitely in both directions. Finally, a quick tip for those problems where you aren't given a direction vector directly. If you are provided with 2 points, you can find the direction vector, b vector, by simply subtracting the position vector of the first point from the position vector of the second point. Now that we have worked through those practical examples, let's pause and consolidate everything we have learned today. Keep these points in mind as we move into our final slide, where I will highlight some common pitfalls to watch out for during your exams. Common mistakes to avoid. Now, as we wrap up this lesson, I want to pause and highlight some common pitfalls. Even if you understand the derivation we did earlier, it is very easy to make small errors that change the entire meaning of your equation. First, be careful not to confuse a and b. I see students swap the fixed point and the direction vector quite often. To keep this straight in your mind, just remember that a represents a specific location, it's your starting point, whereas b represents the direction in which the line is heading. Second, a very critical mistake is forgetting the scalar lambda. If you accidentally write r equals a plus b, you aren't describing a line anymore. You are actually just describing a single stationary point. You must include lambda because that scalar is what allows the vector b to stretch, shrink, or even reverse direction, which is exactly what allows us to cover every single point along that infinite line. Finally, watch out when you are given 2 points, A and B. Some students mistakenly use the position vector of point B as the direction vector. Remember what we practiced in our worked examples. The direction vector, B, is the displacement between the points. You must always calculate B by subtracting the position vector of A from the position vector of B. Keep these tips in mind, and you'll be well on your way to mastering vector equations.